Let's look at some of the example data from my Stanford students. So here's the distribution of homework again in hours per week. And we saw that in an earlier module, the mean homework was 11.4 hours. The standard deviation for homework was actually 10.5 hours. So that's a pretty big variability, right? So on average, students are doing about 11 hours of homework, but the average variability is 10.5. So that means many students were doing down towards 0, and many students were doing 20 or more hours per week. So pretty wide, a pretty large variability here. Let's look at our feelings about math from my Stanford students. So again, pretty wide variability here. I asked the students to rate their feelings about math from 0 being really hate math to 100 being they really love math. And the mean in this particular variable turned out to be 61. So on average, people are favorable, although not highly favorable towards math. But the standard deviation again was fairly high. It was 21. So you can see, on average, people are 61, but it easily goes down to 40 or up to 80. So there's a fairly wide spread here. Now, I mentioned in an earlier module that the feelings about math variable actually is roughly follows a bell curve. It's not a perfect bell curve by any means, but of the variables I've talked about this week, it was one of the closest in terms of following a bell curve. So I just want to pause for a minute, and I'm going to revisit a rule I told you about earlier this week about bell curves, about normal curves. So remember I mentioned that bell curves have this predictable behavior. If you're on a perfect bell curve, you follow something called the 68, 95, 99.7 rule. 68% of the observations lie within one standard deviation of the mean. 95% of observations will lie within 2 standard deviations of the mean, and 99.7% of observations will lie within 3 standard deviations of the mean. If you're on a perfect bell curve, and a bell curve is just a mathematical function, if you follow that perfect bell curve mathematical function, those will be exact. Of course, real data is never going to follow a bell curve perfectly like that. So let's look, see how good this rule is for some real data that looks kind of on a bell curve, but certainly not perfect. How good is that rule for some real data that's not even perfectly on a bell curve? So we can test that out. So the mean here was 61. So one standard deviation below the mean, and the standard deviation was 21. So one standard deviation below the mean is 40. One standard deviation above the mean is 61 plus 21, which is 82. So if you're going from one standard deviation below to one standard deviation above the mean, that's anywhere between 40 to 82. So I actually went into my data set and I looked and counted up how many of my 50 students fell between values of 40 and 82. I actually counted it up. And it turned out there were 34 out of 47. In fact, 3 people did not answer this question, so I only had 47 total for this question, but 34 of them had values between 40 and 82. That's 72%. So it's not 68%, but it's pretty close. If you go out 2 standard deviations from the mean, that gets you out to 100 on the right side, because you can't get it by a higher than 100, and it gets you down to 19. So 61 minus 42 is 19. 19 on the other side. And if I count out the number of students that fall between 19 and 100 in my data set, it was 46 out of 47, or 98%. So again, on a bell curve, a perfect bell curve, it's going to be 95%. With real data that was kind of a bell curve, it's pretty close. It's 98%. And of course, if I go out 3 standard deviations above and below the mean, I cover the entire range, 0 to 100. And of course, that means 100% of my students fell within that range. It's supposed to be 99.7%, 100% is really, really close. So hey, this rule for a perfect bell curve is 95, 68, 95, 99.7. For my real data that's not a perfect bell curve, it came out to be 72, 98, 100, so it's pretty close. Now, I mentioned in an earlier module that binary variables can be thought of as 0-1 variables. You can code them as 0-1s and think of those 0s and 1s as numbers. And we saw that a binary variable has a mean and a median. Does it also have a standard deviation? Sure, of course. If you think of it as 0s and 1s, you can also calculate the standard deviation. So here again is my binary variable, whether or not you played varsity sports in high school. And I had 30 who did and 20 who did not. How would we calculate the standard deviation here? We calculated in an earlier module that the mean is 0.6. So we can subtract each observation from the mean. The mean is 0.6, and everybody is either a 1 or a 0, so it actually makes this calculation fairly easy to do by hand. So if you're a 1, if you played varsity sports in high school and you subtract 0.6, That's a value of 0.4. You then square it. And there's 30 people that have that identical value, so we can just do that once and multiply by 30. If you're a 0, if you didn't play varsity sports, then your deviation is negative 0.6. You square that, and there's 20 of those, so we multiply that by 20. We add all those up and divide by 50 minus 1, n minus 1, and then we square root it to get back to the standard deviation. We come out with a value of 0.49. So what does that 0.49 mean? Well, remember the average here is 0.6. Everybody is either a 0 or a 1, so you're either 0.6 away from the mean or 0.4 away from the mean, so 0.49 is kind of the middle of those. Just to help you understand standard deviation even a little better, let me just present to you 3 simple little mock data sets, and they all have the same mean of 15. They're just 8 people in each of these data sets, but they all have the same mean, but they have different standard deviations. So in the first data set B over to the left of your screen, the mean is 15, but everybody's really clustered around the mean. So the standard deviation is only 0.9. In the middle one, data set A, the mean again is 15, but there's more spread around the mean. So that standard increases the standard deviation to 3.7. In the final data set C, over to the right of your screen, the mean is 15, but the standard deviation is 5.1, because you can see nobody's even close to the mean. Everybody's way out in the tails, and that can happen in a distribution, so that's going to make the standard deviation even bigger. So that's giving you a sense of what the standard deviation means intuitively. Now, we're going to talk a lot about something called the standard error in this class, but I just want to point out now to you the difference between the standard deviation and standard error, because a lot of people get these confused, and I'm going to come back to this, so this is not the last time you're going to hear this, but it's worth me putting this in your head right now as we're talking about standard deviations. So what's a standard deviation and what's a standard error? So a standard deviation that we've been talking about today is a measure of the variability of a trait. So that would be if we're measuring like the variability of how much homework you do per week. The standard error is measuring the variability of something very specific. It's a measure of the variability of a statistic. So when you talk about standard error, you're talking only about the variability of a statistic. And what does it mean for a statistic to have variability? So again, as I mentioned earlier this week, statistics actually follow distributions, but that's a theoretical construct. It's something that we're going to talk a lot about in this course. But statistics follow distributions, so statistics have a shape of the distribution and they have a variability. That variability is called a standard error. Different statistics have different standard errors. So you may have the standard error of a mean, you may have the standard error of an odds ratio, and you may have the standard error of a regression coefficient. Those will all be different. Again, standard error is about the variability of a statistic. And we usually reserve the term standard deviation to talk about the variability of a trait so that we don't get it confused with standard error. I don't expect you to completely understand that yet, but just tuck it away in the back of your head, and we're going to return to this concept a lot in future weeks. Okay, another way to measure the spread or variability of the data is just to rank the data and look at percentiles. We did this when we looked at box plots. So you can talk about things like the 90th percentile of the data. Where does the 90th percentile lie? That will give you some information, some feeling about the data. So the 90th percentile is the value for which 90% of observations are lower. You can talk about the 10th percentile of the data. That would be the value for which 10% of the observations are lower. We've already talked about the median. That's the 50th percentile. Half are above and half are below the median. So sometimes we'll just talk about where those different percentiles lie to give ourselves a sense of the spread of the data. Percentiles will not be affected by extreme values as we saw with the median. So that's going to be different than standard deviations. So that might be a reason that you focus on percentiles, is if you have extreme values and skew data, the standard deviation might be a little misleading. You might instead focus on percentiles. And in particular, one measure that's based on percentiles that we use a lot for describing the variability of data is something called the interquartile range. And we saw this when we talked about box plots already this week. The interquartile range is just the distance between the 75th percentile and the 25th percentile, or also known as the third quartile and the first quartile. It's the middle 50% of the data. And again, that interquartile range is not going to be affected by outliers, because the middle 50% of the data is going to be the same middle 50% of the data, no matter how high or low the minimum and maximum values are. We saw the interquartile range again when we looked at Boxplot. So here is the Boxplot of political bent in my Stanford students. 0 was the most conservative, 100 was the most liberal. And again, the middle 50% of the data lay between 68 and 85, so most students in the liberal and democratic range. And so we would subtract those two values to get the interquartile range, which I abbreviate as IQR, and that value comes out to be 17. So that gives you a sense of the spread of the data as well, that middle 50% of the data in this case is pretty tight. So I just want to summarize here, wrap up with all the symbols that I've thrown at you because I will be using some of these symbols throughout this course. So when I talked about the sample variance, I abbreviated that as S squared. When I talked about the sample standard deviation, I abbreviated that as an S. I want to throw out here now, because sometimes when I talk about variance or standard deviation, I may instead use the Greek symbol sigma and sigma squared. When I'm using a sigma or a sigma squared, I'm talking about a variance that's not calculated from data. It's something that's a theoretical variance, like if you knew the exact distribution. When we talk about probability, this may come up. Or if you knew the true variance in the entire population, not from a sample, but from everybody, you would abbreviate that with a sigma. So that's the distinction there that may come up. When we talk about the sample mean, we represent that with an X bar. So a little bar over my X, that represents the sample mean. Again, mean calculated from data. When I talk about a population or a true mean, which is usually a theoretical thing, I might use instead the Greek symbol mu, which is represented there. And again, the interquartile range I'll abbreviate as IQR.